So today's lecture is going to be about bivariate expectation and conditional distributions. So we'll start off with bivariate expectation. We've talked a little bit about bivariate random variables, marginal distributions, and now we can talk about what expectation means in the context of a bivariate random variable. So we'll start off with a definition, which is bivariate expectation. And our definition is that if we have a bivariate random variable, two components, x comma y, and we have a function g, and g is going to be function from R2 to R, so a two-component real valued function, then we define the expected value of g of x comma y as, well, there are two cases here. In the discrete case, it's going to be the sum over x and the sum over y. So all values x in the support of x and y in the support of y, of g of x comma y times the joint Pmf x comma y. So this looks a lot like the law of the unconscious statistician, and from our univariate case. In the continuous case, it's going to be the double integral. So we're integrating over R2 of g of x comma y times f of x comma y, and then either dx dy or dy dx, whichever order you want. So recall that in the univariate case, if we looked at the expected value of g of x, this was, well, in the discrete case, it was a sum over x of g of x, f of x, and in the continuous case, it was the integral of g of x, f of x, dx, right? And so this bivariate expectation definition is very similar to this univariate case. This was this so-called univariate case we call the law of the unconscious statistician. And in the bivariate case, we have a very similar thing, but now we have a two-variable function, g of x comma y, and our Pmf, or PDF, is also two-variable, f of x comma y. So let's look at an example, a discrete case example. So example. Let us look at a bivariate random variable, x comma y, where x is the sum of two dice rolls, and y is the absolute value of the difference between the rolls. So quick examples of this are, I could roll 1 could be 1, roll 2 could also be 1. This would say that x in that case would be the sum is 2, and y in this case is the absolute value of the difference, which is 0. And our Pmf, so the support here, so support in the x case, the sum of the two dice can be anything from 2 all the way up to 12. And in the y case, the absolute value of the difference can be anything from 0 all the way up to 5. And okay, so other rolls we could get. So, well, first let's talk about what f of x comma y in this case would be, right? So this corresponds to the roll 1, 1. We have a 1 out of 36 chance of getting that. So we could write f of x is 2 and y is 0. Other situations we can get, our first roll could be what do we want? A 5, and our second roll could be a 1. In this case, the sum of the two of them is 6, and the difference of the two of them is 4. And in this case, f of f of 6 comma 4 is actually going to be 2/36, because I could alternatively, instead of getting 5, 1, I could get 1, 5. That would also lead to the sum being 6 and the difference being 4, or the absolute value of the difference being 4. And then, of course, there are situations like f of 3, 0, that has probability 0 happening. This would say the sum is 3 and the difference is 0. And that's not going to be possible. So we'll get, so the PMF outside of certain combinations that are possible is just going to be 0. And we could make a little table of our bivariate, right? So bivariate discrete random variables, we can make a little table. So let's put y as the rows and x as the columns. So x can go anything from 2 all the way up to 12. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And our table for y, we can of course get anything from y can be 0, the difference can be 0, the difference can be 1, the difference could be 2, the difference could be 3, 4, or the difference could be at most 5, right? 5, a difference of 5 would be like 1, 6 or 6, 1. Certain of these things are going to have 0 probability of happening. Let's fill in the ones that have a positive probability of happening. So if the difference, so this is the absolute value of the difference, absolute value of difference, and this is the sum, is the x. So let's look at this. So which ones of these can we fill in? Okay, if the sum here is 0, well, oh, I'm sorry, if the difference is 0, so if y is 0, so let's do the first row, y being 0. There is one combination, let's just look at it, there's 136, we end up there. So the difference is that would be the roll 1, 1. Or we could get the roll 2, 2. Or we could go to the roll 3, 3. Or we can get the roll 4, 4, 5, 5, or 6, 6, right? And that would lead to the sum being 2, 4, 6, 8, 10, 12, respectively, and the difference would be 0, because it's doubles, right? So this first box here corresponds to the roll 1, 1. This second box here corresponds to the roll 2, 2, right? Okay. If the difference, absolute value of the difference is 1, if the difference is 1, so the difference is an odd number, the absolute value of the difference is an odd number, we know the sum also has to be odd. That's a little number theory fact. So we're either at 3, 5, 7, 9, or 11. And we're going to get 2/36 in each of these, right? So if the difference is 1 and the sum is 3, that would be 1, 2, or 2, 1. If the difference is 1 and the sum is 5, that would be 2, 3, and 3, 2. So 2 out of our 36 possibilities. And you can fill in the rest of the table this way. And we'll start to see less and less possibilities have non-zero probabilities who go down this chart row-wise. If the difference is 2, okay, so the difference is an even number, so the sum better be an even number. But if the difference is 2, the sum can also be 2. So that's not possible. We can't have the sum be 3 if the difference is 2, because we can't have an even number and an odd number. And we could have, say, 4. So we could have the difference being 2 and the sum being 4. What would that look at? Like 1, 3, or 3, 1. Difference is 2, sum is 4. And so we'll have 2 over 36 possibilities there. And I won't go through every possible combination here. There's a little pattern that we'll fill out here And you can think about that there are going to be basically two combinations for all these remaining, and we're going to get fewer and fewer combinations as we go. So that's going to be the PMF. It's 0 everywhere I haven't filled in. And okay, so that's just this is the table of our joint distribution, or joint PMF f of x, y, and where this is our values of y and our columns are values of x. If we want to say we can look at, say, the expected value of x, y, so the product of x, y. This will be the sum, the double sum. X goes from, what can we sum? We can sum all the way from 2 to 12. And y could possibly go from 0 to 5. And it's going to be x comma y, so that's our function here, times the joint PMF, f of x comma y. So at this point here, it's just going to be a little exercise in adding together some numbers. I think if you do this out, you get about 245 out of 18. Now that's not less than 1, but this is not a probability, it's an expected value, so that's okay. And so I'll leave for you to fill in those steps there. But we have the whole table, and then you just have to sum x times y, right? So let me just do it the first couple steps, right? You're going to get some terms like, okay, so when x is 2, it's 2, and y is 0, 0, so 2 times 0 times f of 2, 0. F of 2, 0 is 1/36. So this here is 1/36 plus 2 times 1, f of 2, 1. F of 2, 1 is 0. That would be that one there. So that term will actually go away. So you get a lot of things dropping out, but you do the sum, and that should give you, hopefully, what I got here, which is 245 by 18. And at that point, it's just an arithmetic problem. Okay. So what are the other theorems? We had a whole bunch of facts we knew in the univariate case about expectation. So properties, let's just write this as a simple theorem. So theorem, what kind of properties do we know about bivariate expectation? And so we're going to say E is linear. So like the kind of overriding fact we knew about univariate expectation was that that it was a linear operator, and this is true also in the bivariate case. So if we have two functions, let's say g1, which is a two-variable function, r2 to r, and g2 is also a two-variable function, r2 to r, then for any, let's say, two constants, a, b, and r, we have the following fact, which is the expected value of a g1 of x comma y plus b g2 of x comma y. We can just basically distribute this expected value over the addition and over the multiplication by the constants. So this is a expected value of g1 x y plus b expected value of g2 of x comma y. So this is kind of an overarching theorem. There are some simpler cases, say if g1 and g2 were the constant function. This covers cases of like a g1 of x, y plus some constant, right? So the whole thing could be a constant, but this is kind of an overarching case, and for particular choices of g1 and g2, it simplified it to some other facts that we know. But that's kind of the overarching theorem, and the proof of this this linearity fact. Again, just let's say as in the univariate case, this comes from linearity of addition or sums in the discrete case and integration in the so this is discrete case and integration in the continuous case. We know that now it's just two integrals, but two integrals kind of behave in the same linear way as one integral, right? So this would be like a double integral of a g1 x, or a g1 of x y plus b g2 of x comma y dx dy, and we can certainly break this up into a double integral of g1 x y. Oops, I forgot my f of x. It should be an f of x y dx dy, right? We can certainly break this integral up like this, dx dy, plus b double integral g2 x y f of x y dx dy, right? And so this first thing here is this first term here, and the sum of these two things is these two expectations, right? And you can imagine you can replace integrals with two sums to the sigma notation. It's all going to go through in the same way. So the same as the univariate case, theorem basically says expectation, anything that's a linear function, we can nicely distribute over. And g1, g2 don't have to be linear functions, but the addition sign and the multiplication don't pose a problem for expected value, even in the bivariate case. Okay. So that's a nice theorem. Now that we have a theory of kind of bivariate random variables and we have a definition of bivariate expectation, we can start to define some of the familiar quantities that we're used to in statistics, and we're going to define them now in a rigorous way. So the first thing we're going to start with is covariance. Covariance is like the ugly step sibling of correlation. You hear a lot about correlation. Covariance is kind of the underlying concept here. And we define the covariance between two random variables, x and y, or two components of a bivariate random variable, however you want to think about it, as, and we write it COV x comma y, and this is defined to be the expected value of x minus its expected value times y minus its expected value. So it's e of x minus e of x times y minus e of y, right? Remember that e, you could call e of x just mu sub x. It's a constant. This is some number in R, so it's just a constant. And similarly, you could say mu sub y is the expected value of y. Again, just some number that we know. So you could alternatively rewrite this as the expected value of x minus mu sub x times y minus mu sub y. And we know how to calculate this now, actually, because this thing is a certain function. This is, we could say this is the expected value of g of x comma y. It's a bivariate function, or it's a two-variable function where g of x comma y is x minus mu x times y minus mu y, as it were. Oops, get my notation right. Okay, right, and so this is e of a two-variable function of my random variables. That's the two-variable function that is equivalent to my definition. So this is the definition. And below that is just some equivalencies. Of course, we know how to calculate e of g of x comma y because we have a definition all the way up at the top that we started off today with. And so this definition here gives us a way of calculating. If we know the joint PDF, then we can either do some sums or do some integration, and we can find what the covariance is. So the covariance looks a lot like variance, and some facts to keep in mind. So let's just write these as facts. Recall that we define the variance of just a univariate random variable x as the expected value of x minus its expectation squared. And so if we can notice that the above formula says that the variance of x can be calculated as the covariance of x with itself. So covariance generalizes variance to two variables. If I take the covariance of a random variable with itself, that's just called variance. Covariance measures how two random variables change. If they change linearly with each other, you have a high covariance in absolute value. If you have a low, if they don't move linearly with each other, then they have a low covariance. So covariance kind of generalizes variance. And you can see that instead of x minus ex squared, it's x minus ex times y minus ey. So it's kind of a nice little generalization. And the picture, we could look at high covariance. So you imagine if you have sample, this is kind of the sample statistics. High covariance means that x and y kind of move linearly with each other, so they're kind of approximately in some line, whereas low covariance means that they don't have any relation. So if you imagine take samples, if they kind of fall on some line like that, okay, they have a high covariance, and if they fall kind of, there's no relation between them, x and y don't move together, then they're going to have a low covariance. And you can actually see that from the formula, because what am I looking at? I'm looking at, basically what I do is I center x and y, so I subtract off their means, and if x tends to be above its mean when y tends to be above its mean, then x minus the mean times y minus the mean is going to be large, and so we're going to get a high covariance. If x is above its mean, and when y tends to be below its mean, we'll get a very big negative number, so we'll get a negative covariance, which just means they move in opposite directions. And if there is no relation, when x is above its mean, y isn't typically above its mean and below its mean, you're going to get something near 0, because y minus e of y is going to be somewhere around 0. So this is a high covariance. We could say positive covariance, and you could also have something like this, where this is a high negative covariance. And so you get a negative relationship between x and y. And it's basically measuring if, when x is above its mean, does y also tend to be above its mean? When x is below its mean, does y also tend to be below its mean? Or when x is above its mean, does y tend to be below its mean? When x is below its mean, and y is above its mean, so that would be a negative relationship. If there is no relationship, kind of general rule, you'll get something low, and there'll be no real strong relation. So that's the intuition of covariance. But the formula is just this formula, which is a generalization of variance. Okay. So what are some facts? Well, people tend not to want to work with covariance. We tend to work with basically a normalized covariance, and that is called correlation. And so there is no bound on covariance, and so it's hard to compare covariance of one set of variables with another set of variables, because covariance could be very, very large. It's going to depend on the scale of the variable. If I multiply x, if I go back up to my formula, I multiply x times 5 here, and my e of x will increase by 5, and my whole covariance will increase by a factor of 5. And so it just depends on the scale of the variables. We want something that's kind of scale invariant. And so that's where the definition of covariance is, and basically or correlation is. And correlation, so we rescale covariance to be in the interval -1 to 1. 1 meaning a strong positive relationship between the two variables, -1 meaning a very strong negative relationship, and 0 meaning basically no linear relationship between the two things. So the correct way to define this is that correlation, which we denote as COR of x and y, is defined, we take the covariance of x and y and we divide through, I'll write it like this, we divide through by the square root of the variance of x times the variance of y, or equivalently, we could say it's the covariance of x, covariance of x comma y divided through by the standard deviation of x times the standard deviation of y. Standard deviation of x, to the aside here, is we're just basically defining SD of x or y to be the square root of our variance, and equivalently for y. So that's just a definition. Nothing too fancy, but this is how we define correlation, and what's going to happen is this is going to scale, as a claim will show, is that this will scale covariance to always be between -1 and 1. So if I want to compare to the correlation between x and y and z, they're going to be on the same scale, whereas covariance might not be on the same scale, so it's going to be kind of harder to work with. So let's look at some facts of correlation and covariance. Here's our first theorem. So first we're going to go back to variance, and we're going to say if we have two constants, a, b, and r, then if I look at the variance of ax plus by, this is going to be a squared variance of x plus b squared variance of y plus 2ab covariance of x, y. So we're going to build up some facts about covariance correlation. First, we need to talk about variance. That shows up in the correlation formula. And so we can talk about the variance of ax plus by. Ax plus by is a univariate random variable, and so it has a variance. And its variance is given by this formula that is related to the variance of x, the variance of y, and now the covariance. So this is where covariance can start to enter the picture. And so let's look at why this is true, right? So it's not generally true that you can just distribute variance like you can expectation, right? If I ask for the expectation of ax plus by, so this, let me just write this, different than expected value, right? If I ask you for the expected value of ax plus by, our theorem above says that this is aex plus b e y. Very simple. You cannot do that with variance. You can't just distribute it over and pull out constants. You can't even just pull out constants squared. You have to account for how they vary together, so what the covariance is between the two things. So let's look at the proof of this. So proof is not too bad. Let's just define a random variable z. Let's just say that's ax plus by, just for note-taking purposes. And so here we have the expected value of z is ax plus by. And if I want the variance of z, z is just a univariate random variable, I have a formula. It's the expected value of z minus its expected value squared. And we actually know what that thing is, right? We just calculated above. And so if I look at z, which is ax plus by, and if I subtract off, so let's write this is z minus e of z. E of z is a ex plus b ey. And I can rearrange these. I can just do some common factoring. This is a x minus ex plus b y minus ey. Something like that. And now I want to square this thing. So if I look at z minus e of z quantity squared, well, now I just have to square this thing above here. And it's, follows my rule for squaring sums. It's the square of the first, which is a squared e of x squared plus b squared y minus e of y squared. And then I have to include the cross product term, which is 2ab x minus ex y minus ey, right? And so this is like step 1, this is step 2. My third step is that if I want the variance of z, which is ultimately what I want, the variance of ax plus by, I just have to take the expected value of this thing above. And expected value distributes nicely over my linear terms, right? So I'll get a, so the variance of z is, let's just write this out, it's the expected value of z minus e of z quantity squared. And so that's just the expected value of this term here. And so if I apply expected value, I know I can push the expected value through linearly. So this is a bit of notation, but this is just all basically notation. So a squared, I can expected value of that first thing. I can pull the b squared out of the expected value. So I get that. And then I have 2ab, which I can pull out expected value, and I can say expected value, and I'm left over with x minus ex times y minus ey. And now I just have to identify the various parts of this. This first thing here is the variance of x. This thing here is the variance of y. And this, by definition, is the covariance of x and y. So altogether, I get a squared variance of x plus b squared variance of y plus 2ab covariance of x, y. And that's what I claimed, is that if I have the variance of z, which is ax plus by, I get a squared variance of x plus b squared variance of y plus 2ab covariance. The proof is just a lot of notation. Not very complicated, it's just some algebra and knowing that expectation is linear. Okay. So what are some other facts? So that's a fact about variance. What about covariance? Theorem. If A, B, C, and D are some constants, then what do you want to say? Covariance of AX, let's write this, covariance of A plus BX and C plus DY, this is going to be equal to BD covariance of X, Y. So this is very similar to our theorem for variances. For variances, we said that the variance of AX, it would be the variance of A plus BX is going to be B squared variance of X. And in this case, covariance can also ignore additive shift, so the A and the C just disappear. We don't care about addition. And the B and the D come out as constants out front. notice that if I look at the covariance of A, covariance of A plus BX with A plus BX, this is the variance of A plus BX, which is exactly what we get above, right? And that comports exactly with our formula. It would be B times covariance of X and X, or B squared variance of X. So that's the theorem. The theorem basically says that covariance behaves similar to variance in that I can ignore addition, I can ignore adding A or adding C, and I can pull out constants. So what's the proof? Why is that true? If I can prove it for one of the arguments, by symmetry, it can be true for the other argument. So if I were to look at, say, covariance of A plus BX with Z, and Z is some random variable. First, let's look at that. This is the expected value of A plus BX minus the expected value of A plus BX times expected value of times Z minus expectation, Z minus its expectation. So this is all just plugging into our formula for covariance, except now instead of x, y, it's A plus BX and Z. So it's the first one minus expectation times the second one minus expectation. And what happens is I can obviously distribute this inner expectation here over the A plus BX. So we get A plus BX minus A, so minus A plus B expected value of X. And then we're still left with Z minus expected value of Z. Okay. And so our A's will cancel, and we will get expected value of B times X minus EX. So again, just some algebra. So these proofs are real nice because they're just some algebra. And of course, I can bring this B out front if I want. So actually, I can just erase that, put the B out here. This now is B covariance of X and Z. So that's kind of half the proof. I did it for one of the arguments. Shows that I can ignore the A and I can bring the B out as a constant. And so if by symmetry, we can do the same thing for the other, and that will give you the whole proof. So I'll leave it there. You can think about that, but now if I just say, okay, well, let's do the whole same thing and now expand out Z as C plus dy, you'll get the same exact thing. And you'll bring out another D, and you'll just be left with Y there. And then finish, let's just write finish using symmetry. That must be true for the other argument too, and so we're done. Okay, so that's a nice little theorem because it allows us to ignore addition and deal with scaling in covariance really simply. The theorem for correlation is even easier. So the same theorem for correlation basically says we don't care about any of that. If A, B, C, and D are constants, then if we look at the correlation of A plus BX with C plus dy, this is almost just correlation of X and Y. The only thing we have to multiply here is we have to multiply by sine of B times sine of D. So sine of some number, let's say B is just 1 if B is bigger than or equal to 0, and negative 1 if B is less than 0. I guess sometimes people break this out into 3 cases. They'll say 1 if B is bigger than 0, negative 1 if it's less than 0, 0 if b is 0. Okay. So we have to multiply by the sign. So we have to flip the sign. The other way of writing this is that we look at the absolute value of the correlation of a plus bx and c plus dy. That is exactly the same as the absolute value of the correlation of x and y. Right? So correlation doesn't care about addition, say a or c. It doesn't care about scaling either. Right? The whole point of correlation is to not have the metric depend on the scale. So it's not going to care about b or d either. You only care about them up to a sign. Right? If I flip the sign of x, my correlation will change. If I flip the sign of y, my correlation of y will change. Right? So let's say, for example, the correlation of x and negative y is negative the correlation of x and y, right? So I have to flip the signs. I would flip one of the variables. That's why I have this kind of multiplication of sign out front of the sign of the variable. Alternatively, it says up to a sign, the correlation of ax plus b and cx plus d is the same thing as the correlation of x and y. We don't actually care. Up to the sign, they're exactly the same. And the proof of this is real simple because we built up these other facts. The proof is that correlation of x. We want to look at the correlation of correlation of a plus bx and c plus dy. This, by definition, is the covariance of a plus bx c plus dy over the square root of the variance of a plus bx and times the variance of c plus dy. And our top we can deal with if we scroll back up to our theorem. This theorem makes the top really easy to calculate. All I got to do is pull out its BD covariance of x and y. And the bottom, we have our theorem for the variance. It's square root of b squared variance of x, d squared variance of y. And so we get, at the end of the day, b divided by absolute value of b times d divided by absolute value of d. And then we're left with covariance of x, y over square root variance of x times the variance of y. That second term here, this thing, is exactly correlation of x and y. And this is the sine of b and sine of d, right? So the fact that you can think about is absolute value, or is b over absolute value of b is exactly equal to the sine of b. It's going to be plus 1, minus 1, or 0, depending on, I guess, as long as b, if b is 0, you run into a problem, but if b is 0, then we have some other issues going on here. So, okay, so that's a nice and simple proof. Now, the nice thing about correlation, the fact we claimed, so this is all building up to the fact we claimed here, which is that correlation normalizes covariance. So like a normalized version of covariance that has to be between 0 and 1. So how do we show that? The theorem, you could write this, is that the correlation between two random variables x and y is less than or equal to 1 in magnitude. That is, it's between negative 1 and 1. Negative 1 if they're perfectly linearly related, 1 if they're perfectly linearly related, right? Okay, so proof. So how can we do this? Let us linearly transform x and y. So let us call, let's say, x tilde is x minus its mean divided by the standard deviation of x. If I do this, this is basically a z-score, then the variance of x tilde is 1, and the expected value of x tilde is 0. And I'll let you think about why that's true. That's just applying the previous formulas. But so z-scores force the variance to be 1, the expected value of the mean to be 0. And we can similarly look at y tilde is y minus its mean over its standard deviation. Okay. We can do this in linear transformation because it turns out that the correlation between x and y, we know these are linear transformations. And so we have a theorem, in fact, this theorem, that says if I linearly transform x and y, it doesn't change the correlation. So let's put it this way, the absolute value of the correlation of x and y is the same thing as the absolute value of the correlation of x tilde and y tilde, because those are just linear transformations. You have to figure out, the slope is like 1 over standard deviation, and the intercept is negative mean over standard deviation. Okay, so we can actually, alternatively say, without loss of generality, you can just assume that the variance is 1 and the expected value is 0. Okay, and so let's call this rho. So rho is some number that is bigger than or equal to 0. Bigger than or equal to 0 because we've taken the absolute value here, right? And the correlation is the same, so we're just going to instead work with the version of x and y where we've mean centered and made it have a unit variance. Okay, so what if I now look at variance of x tilde plus y tilde? We have a formula that says this is the variance of x tilde plus the variance of y tilde plus 2 times the covariance of x tilde and y tilde. And similarly, if I look at the variance of x tilde minus y tilde, this is the variance of x tilde plus the variance of y tilde minus 2 times the covariance of x tilde and y tilde. So this is our theorem way back up. Let's see if we can find it. Way scrolling back up. Where did we write this? It's the definition. Here we go. This one. So we're using this theorem. All right. 2 where a and b are 1, and b might be negative 1. So that theorem, we apply it. And when we apply it, we get this fact. And we know that the variance of x tilde and y tilde are 1, and the covariance, let's just look at the covariance of x tilde and y tilde is actually going to be the same thing as the correlation between them, right? This is the covariance in this case is equal to the correlation. And why is that true? Because we can, to get one from the other, we have to divide through by the square of the variances, but the variances are all 1. And so there's actually no difference between them, right? So you can look back at the definition of correlation. It's covariance divided through, in this case, 1 times 1, and you take a square root, right? So this is equal to rho, which is we define to be the absolute value of the correlation. It doesn't matter if you have rho or minus rho, it doesn't really matter. But the more kind of general fact is that we can say x tilde plus y tilde, the variance of, let's say, x tilde plus or minus y tilde is 1, which is the variance of x, plus 1, the variance of y, and then it's either plus or minus 2 times rho, because rho is this covariance, or equivalently correlation. So this is 2 times 1 plus or minus rho. And we know that variance always has to be positive. So what we get is that 2 times 1 plus or minus rho is bigger than or equal to 0, or 1 plus or minus rho is bigger than or equal to 0. And what does that mean? That means that rho in absolute value better be less than or equal to 1, which is what we claimed. Think about why that is true. For example, if rho is positive, then we have, if we look at the number line, we have 1, we have 0, and 1 minus rho better be bigger than 0. And which means that rho is less than 1. Or if rho is negative, you get 1 plus rho is bigger than 0. In either case, you can convince yourself that this condition, that 1 plus or minus rho being bigger than 0, means that rho has to be in absolute value less than 1, and that's what we claimed, because rho was how we defined to be the correlation between x and y, right, in this line here. So that proves the kind of fundamental fact here is that the correlation between two random variables is always between -1 and 1, or an absolute value is always less than 1. That's the fact we claimed, which was that correlation is kind of a normalized covariance. Okay, so 2 more things about correlation and covariance we want to talk about. The first one is we have a shortcut formula, like we had for variance. So it's a shortcut formula. For variance, we had that the variance of x, so let's say recall that the variance of x, we had a shortcut formula, we could say e of x squared minus e of x squared. And now we can say that the covariance between two random variables x and y is the expected value of x times y minus the expected value of x times the expected value of y. So this is directly a generalization of the previous theorem. Again, variance or covariance of x and x will give us this. So if x and y are the same thing, if x is equal to y, then that reduces to the previous formula. And so it gives us a real nice shortcut way of calculating the covariance. Proof, real simple, just as simple as the variance case. Covariance of x and y is expected value of x minus its expectation times y minus its expectation. Square it all out. Let's just distribute this all out. You get xy minus x expected value of y minus y expected value of x plus expected value of x times expected value of y. And we know that we can distribute this expected value linearly over all these terms. So I get e x y. Expected value of x times expected value of y. Expected value of y is a constant that comes out. So that can be written as expected value of x, expected value of y, minus expected value of y, expected value of x, which is this third term. And then we have our last term, which is just a constant, so taking its expectation doesn't actually do anything. And so we get expected value of xy minus expected value of x times y minus expected value of y times expected value of x plus expected value of x minus expected value of y, right? One of these is going to cancel, and that leaves us with a formula. It's this thing minus that thing. So we can look at an example of this in action. Let's look at a nice example that kind of ties together a lot of the things we've been talking about so far. So example. Okay. We're going to let x and y be our bivariate random variable. And this is going to have a PDF. So I'm telling you it's continuous. Of my joint PDF is 1. And this is going to be true when x is between 0 and 1, and when y is between x and x plus 1. So let's draw that region. What are we going to show? This region is, if this is 0 and this is 1, so x can be between 0 and 1, y is going to be between, so if this is the line y is equal to x, and this is the line y is equal to x plus 1, then this kind of trapezoid is our region. And so our PDF, our joint PDF, is 1 everywhere in this region and 0 outside that region. All right, so it just defines a bivariate density. You can convince yourself this is true, that this is a true real density, but it's pretty simple. It's just basically uniformly distributed, not over a square, but over this trapezoid. And so let's calculate, in this case, let's calculate the correlation between x and y. Are x and y correlated? I don't know. It seems like they should be. There's some relationship between them. Y is always between x and x plus 1. So what do we need? To do this, what we can do is we can write this as the covariance of x and y over the square root of the variance of x times the variance of y. And so we get the marginal of x and the marginal of y, we calculate the variances, and we can use our shortcut formula to say this is e of xy minus ex times ey divided by square root var x variance of y. Okay. And so if we can get this, let's write this a little more legibly here. We can get this and this term and the whole bottom, and get all of these from the marginal distributions. So if I can calculate the marginal distributions of x and y, then I can get ex, I can get ey, I can variance of x, variance of y, and now all that leaves is this ex times y, which is just the last thing I'll need to calculate. And no way around that. That's just going to be a straightforward calculation. So let's first just get the marginal distributions of x and y. Marginal of x. Let's get that first. Okay. So we know we can get the marginal PDF of x. This is the integral of f of xy. We integrate out y, right? And in this case, if we look at our picture, y goes from x to x plus 1. The PDF is 0, and we integrate with respect to dy. So this just gives us y evaluated from x plus 1, and that just gives us 1, right? It's going to be x plus 1 minus x, which is 1. And this is true as long as x is between 0 and 1, i.e., this says that x is uniformly distributed over 0 to 1. So actually the marginal distribution of x is uniform. And marginally x is uniform between 0 and 1. All right? So if you just kind of project it down onto this x-axis, x is just uniformly distributed between 0 and 1. Y won't be, because it has a weird kind of trapezoidal relationship with, or trapezoid's not the right word. Why am I using that? Rhombus relationship, square relationship with x. Okay, but that gives us the marginal of x, which means we have two of our quantities basically for free. We know that expected value of x is 1/2, and the variance of x is 1/12, right? And we know that based on our previous lecture on the continuous uniform. Okay, we now want to get the marginal of y, the marginal distribution of y. Kind of similar process. F of y is we take the joint and we integrate out x. This will have two cases. So there are going to be two cases here. If y is between 0 and 1, so let's go back up to our picture here. If so this is kind of the value here. How do I want to draw this? If we're kind of in this region here, right? So if y, my picture is fairly poorly drawn. It doesn't look like what it should look like. Maybe I can redraw our picture here. I think it has to be more. So let's just draw this a little bit better. I think it has to be like this. That's accurate representation. Okay, that's a more accurate representation. All right. Okay, so if y is between 0 and 1, then x goes from 0 to y, right? If y is here, x goes 0 to this point, which is the point y is equal to x. So in this case, it's the integral of our joint PDF, which is just 1, and it goes from 0 to y integrate with respect to dx. That just gives us y. And in the other case, it's still going to be the integral of that PDF, but now our bounds are going to be different. If y is between, it could go all the way up to, so this would be 2 here. If y is between 1 and 2, at each y here, say, we will go from this point, which is x is y minus 1, all the way up to 1. So our bounds are now y minus 1 to 1. On the integral, so my bounds go y minus 1 to 1. And in that case, I do that. I'll leave the calculus for you. That's 2 minus y. And this is for that bound. You can put a less than or equal to if you want. Okay. So all together then our margin of y is y if y is between 0 and 1, and 2 minus y if y is between 1 and 2. That's not a named distribution, I know. I'll leave it to you. So here's your exercise. Why are we getting the margin of y? What we want is we want to get the expected value of y, and we want to get the variance of y. And I'll leave that as an exercise to you. You can show the expected value of y is 1, and the variance is 1/6. So at this point, we've got the denominator here. We've got these two parts up in the numerator for our formula for correlation. We now just need to calculate the expected value of x times y, and this is just going to be a straightforward Calc 3 problem. No tricks here. So the last thing we need, let's do it back here, say last part we want is the expected value of x times y. And if you go back to the very top of our lecture, how do we calculate this? X times y times the joint. And we integrate whatever order we want. I'm going to do dy first. Because it's easier. If I integrate the dy first, our bounds for x goes x plus 1, and y goes, or x goes 0 to 1, right? So if we go back up to our picture here, I'm integrating first with respect to y. So if I were to fix an x, my bound would go x to x plus 1 for each value. And then we integrate from 0 to 1 with respect to x. So y goes x to x plus 1, x goes 0 to 1. So a lot of Calc 3, this is I'll write it like this, Calc 3, and you can check this is an x size for you. That should give you 7/12. And so all together, if we combine everything now, our correlation between x and y is 7/12 minus 1/2 expected value of x, 1 expected value of y, square root of 1/12 is variance of x, and 1/6 is the variance of y. And that is some number. Yeah, that's a number you can calculate that will be positive, right? 7/12 is bigger than 1/2, so it'll be slightly positive, which makes sense. X and y, looking at our picture, kind of move. As if y tends to be larger, x also tends to be larger. Okay, so that's where we're going to stop on bivariate expectation. The next topic we're going to start now, we're going to finish up next time, is we're going to start talking about conditional distributions. So let's see, conditional distributions. So we're going to do some definitions, do maybe 2 examples here, and then we're going to call it quits. So recall that for events, way back when we talked about events, we could calculate, say, the probability of A given B, and it was the probability of A intersect B over the probability of B, right? Now, for discrete, if I have x and y are discrete, and if I let A be the event that x is equal to some little x, and B be the event that y is equal to some little y, then I could calculate the probability, say x is little x given y is little y, as probability A intersect B is x is little x and y is little y. So again, by comma means and then we divide by the probability of y is little y. So that's all nice if things are discrete. And so this basically, we've now formed a way to calculate, to condition one random variable on another, at least in the discrete case. We'll get to the continuous case in a minute. In the discrete case, if I want to talk about the probability x is equal to some random variable little x, given that y is equal to some random variable, or if I want to calculate the probability x is some value little x, given y is some little y, all I have to do is use my formula for events and just define my events nicely. And all this goes through. And so what this allows us to do is to define, so remember the definition here, what is called a conditional Pmf. So this is only for the discrete case right now, conditional Pmf. And the conditional Pmf of x given y is some value little y is defined as, so there's a couple ways we can write this. You could say f of x given y is equal to little y of x, or I could be really lazy and just write f of x bar y, right? So we use this bar notation. This second way is typically how I write it. And this is just going to be the joint Pmf, which is exactly what I wrote here. Probably x is x and y is y, over the marginal Pmf of y, which is exactly in the denominator. probability y is equal to little y. So this thing is called the conditional Pmf of x given y is some value little y. And we can think of, and so it gives us a way of calculating one random variable conditioned on knowing what the value of the other random variable is. In a more general way, you can consider, we could say z, a univariate random variable z, as, quote, x give bar y is little y. So I'm going to write it like this. The quantity x, which is a random variable, given y is some value, we can think of that as a univariate. You consider this as a univariate random variable with Pmf given by the formula. So you can think of, if I condition x on y being some value little y, that gives me a new random variable, a new univariate random variable, x bar y is little y. You can call it z, you can call it whatever you want. But the point is that the Pmf, that this quantity here is a univariate random variable and has a univariate Pmf given by this, and the way we calculate that from the bivariate information is given in the formula or the definition above. Let's look at an example. So, example. So here's our joint Pmf of x and y. Okay. So I'm just going to draw it in a table here. X and y, x can take on 3 values. X can be 0. Let's write it this way. X can be 0, x could be 1, or x could be 2. So this is my values, possible values for x. And y could be 10, y could be 20, or y could be 30. And I'm just going to write the value of the Pmf at each of these points. We're going to say 2/18, probability x is 0, y is 10 is 2/18, probability x is 0, y is 20 is 2/18, 0. I'm just going to fill in the rest of the table real quick here. 18ths, 4/18ths, 3/18ths, 0, 0, 4/18ths. We can check this as a valid Pmf. All these values better sum to 1. We get 4 is 8, plus 6 is 14, plus 4 is 18. So it all sums to 1, so this is a joint Pmf. So these are the values of f of x comma y. And we can get the marginal distribution. So we can get marginal of y, or the marginal of x, right? And we write this in the margins. We do that in the marginal of y, we just sum over x. So this is going to be 7/18, that y is 30, 6/18, that y is 20, and 2/18, that y is, 5/18, not 2/18, 5/18, that y is 10, right? I'm just summing along the rows. And then in the marginal of x, I sum along the columns. So that would be 4/18, that x is 0, sum along that column. Next column is 10/18, and then the last one is 4/18. So this is the marginal of x, and this is the marginal distribution of y, right? And then the blue values are our joint. And I could calculate, I could say, what is f of, let's write it this way. What is the distribution of, let's do this. Let's say y given x is equal to some value little x. Well, we can calculate that for any possible value. Let's say y of f of y given x is 0. The formula for this is f of x, or x, which is 0 in this case, 0y, over f of 0, for our different values of y. And so we basically get a table, and in each point in the table, we're going to fill in, this is f of 1 given x is 0, f f of 10 given x is 0, f of 20 given x is 0, and f of 30 given x is 0. Okay. 10 given x is 0 is f of 0, 10 over f of 0, which is going to be f of 0, fx of 0. Let's write that more formally. This is f sub x. It's 4/18ths. So 4/18ths in the denominator. And in the numerator, we get f of 0, 10. 0, 10 gives us 2/18ths. So this is 2/18ths. Or in total, we get 1/2. And similarly here, we're going to get f of 0, 20 over fx of 20, or I'm sorry, fx of 0, which is, so again, 4/18ths in the denominator. F of 0, f of 0, 20 now is just this next one, is again 2/18, which is 1/2. And we kind of know that this last one has to be 0, right? So the last one, which is f of 30, given x is 0. So the probability that y is 30 given x is 0 is f of 0, 30 divided by fx of 0. 0, 30 is 0. So the whole thing is 0. So this is a marginal distribution. So this is the distribution of, y given x is 0. The probability y is 10 given x is 0 is 1/2. Probability y is 20 given x is 0 is 1/2. Probability y is 30 given x is 0 is 0. So univariate random variable. You could draw the little plot for it. This is f of y 0, and y can take in the values 10, 20, or 30, and it's 1/2, 1/2, 0. So it's just a univariate random variable. So that's how it works for the discrete case. The question arises, what do we do in the continuous case? And so let's talk about that. Continuous case, what we'd like to do is we'd like to say that the probability x is x given y is some little y. Before, what we do is we just say this, x is x and y is y over probability y is y. So the problem now is that probability y is equal to little y is 0 in the continuous case. So we can't define it this way. It kind of formally fails because you can't talk about this in the same way. What we do is we kind of just fudge it. And it works out that kind of in the limit, we can define, and so I'll write this here, the conditional distribution. And this is the continuous case. If, again, we're just going to basically use the same formula as the discrete case, and it works out pretty nicely in the way we want. If x and y are continuous, then we don't get a Pmf. The conditional PDF of x given, let's read PDF. PDF of x given y is equal to some value little y is, so if you look back up at our continuous case, scroll all the way back up, all we do is we take the Pmf, the joint Pmf, and we divide through by the marginal Pmf of y. And in the continuous case, we're just going to replace the Pmfs with the PDFs. So we're going to kind of fudge it, and we can say that x, y, the conditional Pmf of x given y, f of x bar y, is the joint Pmf, or sorry, joint PDF over the marginal PDF. So this is, top is the joint PDF of x and y, and the bottom is the marginal PDF of x and y. But it works out all the same. So it's basically the same formula as in the discrete case, but now we're dealing with PDFs. So you can't interpret them as probabilities. They're kind of densities in that way. Okay, so to close, let's just real quick look at one example. So here's our example. And the example is this. So x comma y has joint PDF of f of x comma y is e to the negative y, and this is true for 0 less than x less than y. So with all these kind of Calc 3-ish problems, what we do is we're going to draw the region. Here's the line y is equal to x, and so we're defining this on this region, right? This is where x is bigger than 0. So this is my x-axis, this is my y-axis. X is bigger than 0, and y is bigger than x. And our joint PMF here is just e to the negative y. So it actually doesn't involve x in that way. Okay. So can we get the conditional distribution of, what do we want? Let us get f of x given y. This is the conditional distribution, i.e. PDF of the random variable x given that y is some value to the y. And our formula says that f of x bar y is the joint, which we have directly, we're given it, c to the negative y, over the marginal fx of x. Okay. So all we really need to do is get the marginal, right? Which is not too bad. So the marginal of x is f of x. Be lazy and maybe not my subscript. What do? I take fx y and I integrate out y. And so what is this integral? For each value of x, I integrate from y is equal to x to infinity, right? So I go from x to infinity. My PDF is e to the negative y, integrate respect to y. That will give me, I'm going to skip some steps here, but that will give me e to the negative x. And so f of x bar y is the joint, e to the negative y, over the marginal, e to the negative x. Or this is equal to e to the x minus y. And this is true as long as 0 less than x less than y. All right. My marginal PDF outside of the support of y, say, is going to be 0. So I can't divide through by 0, right? This formula break down. Ooh, I wrote this backwards. This is the, let's back up here. Anyone catch this error? This is the, really I'm calculating y given x is little x. So let's back up. This is y given x, right? Because x is in the denominator here, right? So this is f of y given x, sorry. Okay, everything else holds though. Yeah, we want y given x. Okay, but that's a nice little example. This looks like an exponential distribution. The exponential distribution is like e to the negative y, right? And it's called a shifted exponential. And so typically the graph of an exponential, the PDF of an exponential distribution, looks like this. So this is our PDF. And what ours looks like is if I start at the value x, it goes like that, starting at x instead of starting at 0. And so this is f of y given x. So y given x is some value little x. It has a shifted exponential distribution. So it's basically an exponential, but instead of starting at 0, it starts now at x. So that's kind of cute, right? So all that's happening in this case is if I condition on knowing where x is, my exponential distribution starts at x. Okay, so I'm going to stop there because we're out of time. So that's our introduction. We've done the bivariate expectation, and we've also now started to talk about conditional distributions. And so I bet you can guess next time we're going to talk about conditional expectation. Of course, these are random variables. We can talk about expectation, and then the follow-up on conditional probability was independence, and we're going to talk about independent random variables, and that is one of the more important topics in the course. All right, and I'll stop there.